Okay, can everyone hear me? Even in the back? Sounds good? Cool. All right, so I'm James Munns, and this is my talk called Life Before Main. So, this talk is sort of about embedded development in Rust, but not entirely. A lot of it's totally true whether you're writing C or Rust for embedded systems or on a desktop. But I want to investigate everything that happens before when you start running your program and you execute the first line of main. So a little bit about me. I'm James Munns. I'm BitShiftMask on Twitter. I talk a lot about embedded stuff, so if that's your kind of thing, I would recommend following me. I work for a company upstairs called Ferris Systems. We're a software consultancy focused on system development in Rust. So whether that's embedded systems, distributed databases, any kinds of fun, hard, low-level problems in Rust, we help out with those kind of things. So, actually, before I get started, how many people here have, we'll start, who here has written Rust before? All right, for the camera, that's almost everyone in the room, at least most people. How many people have written microcontroller code before? Okay, we've got like a third of the room. How many people know what a microcontroller is? Okay, again, most of the room. So for anyone who didn't raise their hands or anyone on the video, a microcontroller is a really tiny little computer system. They typically power almost every computer you don't sit in front of. So whether you have a smartwatch, whether you have a step counter, whether you have an engine control system for your car, that's running code, and it's probably running code on a microcontroller. But we write code for them, but how do they know how to run that code? So when you power these embedded systems on, you connect them to a battery, you plug them into the wall. Step one, apply power. Great, that's definitely where you're going to start. You're going to plug the USB cable in, you're going to flip the switch. Great, makes sense so far. Step two. Step three, run code, profit. This is going to work great. It's going to start running all that embedded code we wrote, and everything's going to work perfectly. But what? What happened in between, like, I started shoving electrons into my system, and then code came out? Well, I mean, there's a couple things that go into this. Let's say we were writing the simplest embedded system in the world. We were writing a blinky light. This is like hello world for embedded systems. A lot of embedded systems don't have a screen, so how do you say hello? Well, if the only thing they have is a light, well, you're going to blink an LED. So in Rust, some blinky LED hello world code might look like this. So we have main, so this is going to feel really familiar whether you've implemented embedded systems or not. Let's see, do I have a laser? I do have a laser pointer. So some of this is specific to Rust, and I'm not going to get into this in this talk, but we have these libraries that tell us how to work with our board. For example, the board I'm using in this demo is a board called the DWM 1001. So we're going to go ahead and grab our drivers for that. We're going to start a timer, and then this is our wonderful masterpiece of code. We have an endless loop that turns an LED on. It waits 20 milliseconds, and then it turns the LED off, and it waits 230 milliseconds. So it's going to go blink, 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 blink over and over again. And this is great. This is a whole functional embedded system. It's the best thing that can ever be shipped. But this is your code. But how does that actually make the whole system go? Well, it's not just your code. If I zoom out on this example a little bit, your code's in main, but also this is Rust, so you've probably included some libraries. So at the top of your file, you might have a line that says this is no standard. We're on an embedded system here. There's no standard library. I'm going to use that DWM 1001. This is where I've defined all my drivers and stuff like that. I didn't have to write it. Someone else did. I'm also going to pull in this crate called Cortex MRT, specifically the entry macro. So we saw that back on this slide. You know, we got a little entry attribute hanging out on top of main. Panic halt. This says what our embedded system should do if it panics, because again, this is an embedded system and there's no operating system. So if you panic, normally your application is stopped by the operating system and everything stops. But if you don't have an operating system, you've got to tell the embedded system how to do this. And then we pull in some other things specifically about the driver. But we still haven't answered what happened, so we've got some more code. We know there's more code involved now because this is Rust and we have a library pulled in and things like that. But what are all the parts that take the code you write, that 10 lines of main or whatever I had? I'm going to move this away from my mouth because it's popping a little bit. What makes it actually run on your hardware? Well, there's a couple parts that go into this. There's code, So a little bit of your code, you write the main, you define the business logic and stuff like that, but a lot of other people's code. And you didn't see that because we just pulled those in as crates, but we'll get into that. The compiler helps. So from the Rust side, the compiler front end, rustc, helps with a bit of this, and then the compiler backend, LLVM, helps out with some of this, but less than you might think. You might think the compiler is pulling all the magic here, but it's really not all of it. We also have the linker. So if you're writing desktop applications, you're still using a linker. Linker is what takes the compiled code and makes your final executable, but you don't think about it very much when you're writing desktop code because it just works and you don't have to interact with it unless you get weird symbols like, I don't know what this is, you need to define this and tell me what it is. But for embedded systems, this does a lot more heavy lifting than you might think. And then finally, you've got the actual hardware. In this case, our embedded system is actually going to do some of this magically for us. When I say magically, we need to put things in the right place, but then it's going to take over the show. And then finally, last, your code. Again, but not as code, as machine code. So this is something that your compiler is going to generate, and it's going to create a bunch of machine code or the output of the compiler, and this is what's going to actually run on your system. This is what's blinking the LED. So I have a slide that says, what is a runtime? Real quick poll. Is Rust a language that has a runtime? Yes, raise your hand. No, raise your hand. Okay, we got more no's. How about C? Is C a language with a runtime? Raise your hand for yes. Raise your hand for no. The people who said yes were right. It doesn't have the same kind of runtime that Python has, where you have an interpreter going out and taking your code and doing something with it and doing a lot of things behind the scene. But there is a runtime. And if there wasn't a runtime, we wouldn't ever be able to execute main because you just have to drop main on the hardware and it would have to go. The runtime that C and Rust have is a little bit different and a lot more lightweight. But there's still a couple things that the language says need to be done before you start writing main. And this is true for an embedded system or your desktop. So I talked about that thing of someone else's code. So at least in embedded systems, the part that's doing the heavy lifting from someone else's code is two libraries. There's Cortex-M RT, RT stands for runtime, and R0, which is if you've ever developed C code and you've seen the word CRT0.o, that's the C runtime, and it's typically provided by your compiler, unless you're doing something really weird, and it's going to be the thing that injects kind of this before main behavior. In Rust, we've written it in Rust, so it's just a standalone crate called R0. So what CRT0 is, or excuse me, CRT0, in Rust, what Cortex-MRT is going to give you is this kind of a function, and I've boiled this down a little bit. But we've got a couple steps that are our launch sequence before we get to main. So the first thing that happens is we power up, and this function starts executing. We in Cortex-MRT give the ability for people to define a pre-init. So if you really have to initialize something on your hardware before anything else happens, maybe you're hooked up to some really high voltage stuff and you need to turn it off when you first power on. You might call the pre-init hook and say, no, do this first. Seriously, nothing else before this. Then we're going to initialize the RAM. And if you've developed on desktops, you've probably not had to think about RAM. You go, okay, RAM is there, and it starts with 0, and all of my static variables are predefined, and they're loaded in when I start running. But something has to do this, because the hardware is not going to do it for you. If we're running on a microcontroller that has a floating point unit, we're going to turn that on just so we can do faster math or math that actually works. And then we call main. Hey, that looks like a normal function call. Great, we're going to jump into main, and that's where your main actually happens. The lights start blinking. Now, I didn't really explain much in that last thing. On these embedded systems, there's a concept called the reset vector. And the reset vector literally is the address of where to jump to in the machine code for where you start running. So a reset vector is literally the hardware boots on, you have an address, and it goes, thank you, and then it jumps to that address like a go-to statement, and it starts running that code. That's called a reset vector. The vector means you go there now. Vectors are not just the reset vector. On a microcontroller, you have a whole thing called a vector table. And this is a definition where you put in all of these kind of vectors. So the reset vector is one of these kind of vectors, but it really is only one of them. There are a bunch of other things like exceptions and interrupts that the hardware is going to need to know how to respond to. And these work a lot like callbacks, where you define a table and you put the address of some function in this whole table, and whenever that event happens, so on JavaScript or something like that, you'd have a callback that gets triggered. Here you have an interrupt that fires, some response to a real hardware stimulus. And this is how the hardware knows to say, oh, that happened, run that code there right now. So this all fits together in a couple different ways. I've talked about, okay, we know that when our system powers on, there's the reset vector and it knows to jump somewhere. But when we compile the code, what is that code, like all of that binary that we've generated, what does that break into? Well, it turns out it breaks down into about 3 big sections. You've got the text section, which is where all of your read-only parts go. So your actual machine code that you generate, your functions, your actual code lives here because you typically don't modify it at runtime. It's read-only. This is something that your CPU is actually going to pull in and start executing it sequentially. Also, anything that is constant, whether you have predefined data, if you've ever seen just strings and you've kind of accidentally typed cat on a binary file and you've seen a bunch of strings interspersed with a bunch of garbage, that's because these constant strings you have are encoded as part of the binary. We have another section called BSS, which stands for Basic Service Segment. I don't remember. It's an archaic term that we still use, but what's that? Maybe? Binary storage space? Okay. I'll have to look at Wikipedia. But this is a chunk of your RAM where everything inside of it is expected to be uninitialized. In C, if you were defining a global variable that you never set to, you just define the global variable, it would go here. And as per C's contract, anything that's uninitialized gets filled with zeros. So whether that's valid for that structure or not, it's going to be full of zeros. Rust, I believe, follows this as well, but it's much harder to make uninitialized structured in Rust. The compiler really doesn't like it. Although now with mem uninitialized, maybe you can be able to do that. And then we have another section of your RAM with .data. So if you had defined a global variable where you say, like, I've got some struct with x, y, and z, and x is 10, and y is 20, and z is 100, then that structure, that global variable, is going to live in RAM. So the actual location of that structure lives in RAM, but those initial values are going to live somewhere else. They're going to live probably in text, where you say, okay, all the initial values are here. When you boot up, take that value, put it there. That way everything's good to go before we get to main. But how does it know where to put stuff? Well, the compiler knows. If you write some code and you compile a function and it makes machine code, it goes, that's machine code. That goes into the text section. And if you define some kind of constant, string or something like that, text section. Global variable without an initializer, BSS. With an initializer, data, or you put the initial value in text and you put the location there. So the compiler knows how to sort these into buckets. It still doesn't know where they should live, but it can go, at least when I'm compiling code, it goes that bucket, that bucket, that bucket. Same with Rust-C, same with LLVM. They know where these things are supposed to go. Okay, so I guess if we fall down the chain, the next thing is the linker. How does the linker know where to put stuff? Because that's the linker's job, is to take those huge buckets of object files that we've created and constants we've created and to put them in the right places to make an actual executable. How does it know? Well, we tell it. Because it can't know by itself. I mean, if you're running on a desktop and there's a predefined place to pull all of these, like if you're running on Windows or running on Linux, it's going to know out of the box. But our embedded systems are kind of special, and every embedded system is a little bit different, and every manufacturer makes their hardware a little bit different. So for embedded applications, we almost always have to tell it where to put all of this stuff. And we do that using something called a linker file. Maybe you've heard of this as a scatter file, but essentially there's a separately syntaxed document that you have to prepare that tells the linker where to put all of these things. If nothing else, where to put each of these categories of things. So this is the part that's applicable to Rust. That Cortex-MRT library that we have provides some magic, mostly through some templates and through using a build.rs script, where they provide some defaults of where do you put this stuff. So Cortex-MRT provides a file called link.x.in. So whenever you see one of these .x files, think linker script. Sometimes they're .x, sometimes they're .ld, but these .x are what we use here for these generated linker scripts. So this is the base template where we say, text goes here, data goes here, BSS goes here. It's kind of the skeleton of where all this goes in a regular embedded system. Some embedded systems, you're going to do some really weird complex stuff, so you might just jump to the end because you've got a hard code where all this stuff is anyway, because you have a really special system. But for most people who are writing blinky lights and even more complex software, they can use this kind of template. The next part is device.x. So like I said, every one of these embedded systems are different. One microcontroller might have 10 interrupts that it can respond to, and another might have 100. And because those all need to go into the vector table, that might be differently sized. So you need somewhere to define, okay, what interrupts does my hardware actually have? You need the memory.x. So even if you have the same chip, a lot of times vendors will sell like a cheaper one with less RAM and flash and a more expensive one with more. So you need to say like, okay, I have 64 kilobytes of flash. That's a lot of flash. Or like 128 kilobytes of RAM. That's a really lot of RAM. And finally, these all get smushed together by a build.rs script, and you end up with a file called link.x. And this is what gets fed into the linker that says, okay, you take all those object files that the compiler is going to give you, you're going to take this configuration file, and that tells you where to search and sort and put things in the right buckets and put them in the right place so you can spit out the final executable that your hardware needs. So the device.x might look like this, where it defines all of these different interrupts. Mine's on an NRF52, which has a radio. So you might have like a power clock interrupt or a radio interrupt, and it's going to provide some kind of default value, but really it's going to list all of these interrupts. So it knows how big that vector table is going to be. And then in memory.x, you might say, oh, and this is what a linker script syntax looks like, by the way. It's kind of reasonable to read, but it's a whole different syntax from any other language. So we might have a section called flash. This is our non-volatile memory. And we're going to say it starts at address 0. So on microcontrollers, they're 32-bit systems. So every address is 0000 to FFFF. And all of these are valid address locations. So we say, because we've read the data sheet, that our flash lives at 0, and we've got 512 kibibytes of it. And RAM lives at 20,000 hex, and it's 64K. So now we've kind of told our linker we've got non-volatile memory here and volatile memory here. So it goes, okay, I know that now. And that link.x in, so this, like I said, it's a skeleton or a template. And I've taken out a lot of the complicated parts, but you can see that there are generally a couple buckets that we define for our linker. We've got that vector table that I talked about. And we say that goes at the top of flash because in a Cortex-M system, there's kind of a contract between you and the hardware that says that vector table always goes at memory address 0. Because when the system boots up, it's going to look at memory address 0 and it's going to start processing that vector table the way that you've defined it. So that lives in flash because flash is the only thing that's persistent across resets because RAM goes away whenever you turn off your power. So we put all of our code in flash, including the vector table. So vector table goes first. Then text. So that's all of your code that you've actually compiled, as well as all of those constants and things like that. Then we scroll down a little bit, and we've got data and BSS, and those are in there too. Oh, the one special thing I wanted to show you here, we've got, oh, is that not updating up there? I guess when I scroll on my presenter. Okay, there's a slightly different syntax. In our data section, we also tell it, hey, the data, the actual variables are going to go in RAM, and the original definitions for it are going to go in flash. So it needs to know definition here, location here. So with all of this put together, an ELF is born. So if you're building an executable and you're using the ELF file format because you're on Linux, this is what actually contains all of that information. It's got all of the binary sections. It's got where they go, their memory addresses. Maybe it has debug information rolled in there. But when you run cargo build, you get an ELF file out that's valid for your microcontroller system. So now we're down to the last part of this system. We've got the hardware. And this is the really magical part because once you put things in the right place, everything just happens. So once we've taken that ELF file and we've used a debugger or a JTAG unit or an SWD unit, we've taken that ELF file, that binary that lives on your hard drive, and we've uploaded it onto our actual microcontroller, and it's been smart enough where it goes, okay, I put the vector table at 0, I put all the other code in there. That vector table points to the reset vector, which is inside of my code. And I've got all of this area of RAM where I'm going to have my information. We go. And the launch sequence looks a little bit like this. So the code exists in Flash, again, after the vector table. So the vector table is up top. The reset vector is called because at the top of Flash, we said, when you boot up, you will call this function first. And it's that reset function that we talked about in Cortex MRT. So it's going to go to that location, and it's going to start running that sequence. Eventually, Cortex M runs reset. Your RAM is set up. And then your main is run, because we've upheld the runtime invariance. Essentially, it was just those two functions that say zero out this chunk of the RAM and copy this chunk of RAM from the Flash section into the RAM section. And then your main is actually run, and like any other Rust program, it just happens. And by the way, this is how it works on microcontrollers, but it's almost exactly the same on your desktop too. Windows and Linux and Mac have slightly different launch sequences, but it's going to be holding these kind of invariants the same because it has to have this runtime behavior. So, and then once we have it all done, let there be blinky light. And there is a blinky light running. I actually have the hardware here. So after the talk, if you want to come up and see exactly how this works, and I can pull up a debugger and we can step through instruction by instruction of how this actually works, I'm happy to sit down and you will end up with a blinky light at the end. So I have not been staring at my time, but thank you very much for listening to me. I have a couple plugs. So one, if you're interested in this kind of stuff, and you're interested in embedded, and you're interested in Rust, I'm part of the embedded working group. Come join us. We're working really hard to make Rust like the best ecosystem for embedded systems development. So if this is the kind of thing that you're interested in working on, then come join us here. I've got a link to our coordination repository. I work for a company called Ferris Systems. Like I said, we do consulting in the area of systems level stuff with Rust, including embedded systems. Not shown here. We're also running a conference at the end of April called Oxidize, which is the first embedded Rust conference, and we're having it here in Berlin. So we're going to be having workshops and talks on embedded Rust, embedded Linux, and bare metal development like this. So if that's the kind of thing that interests you, come talk to me after the talk. And yeah, thank you. That was Life Before Main, and if I still have time, I can go into way more detail of the actual Rust of how this works, but if not, then come find me after the talk, and I'm happy to show you. So, thank you very much.